We'll now have the presentation on the engineering design of Globe Life Field with Jeff Jansing and Boharan Jawbabi with Walter P. Moore. Jeff Jansing, PE, is principal of Walter P. Moore and has experience in structural engineering and analysis and development of a diverse group of project types, including sports, healthcare, aviation, performing arts, parking garages, and hospitality. Jeff joined Walter P. Moore in 2004 after receiving his Bachelor of Science and Master of Engineering degrees from Texas A&M University. Jeff served as the structural project manager for the new Texas Rangers ballpark, Globe Life Field in Arlington, Texas. As project manager, Jeff provided ongoing guidance and insight into the design process and directed the day-to-day efforts of the entire structural engineering design team. Boharan Jawbabi is an associate at Walter P. Moore with experience in complex structural engineering analysis and design of various sports and performing arts projects. He received his undergraduate and graduate degrees in structural engineering from University of Florida. He joined Walter P. Moore after graduation in 2014. He led the analytical design and modeling for the operative roof and supporting rail trusses in the new Texas Ranger ballpark, Globe Life Field. He was a chief collaborator in the development of the digital processes used during design and served as Walter P. Moore's full-time site representative for the span of the construction project.
Thank you for having us here to talk about this very exciting Globe Life Field, the new home of the Texas Rangers. We have this presentation divided into two parts, part one being the bowl structure, and then the second part will be discussing the roof structure. We'll be hitting some of the site items, and then we'll focus on some specific items that we thought it might be of interest to you. Due to the very large, complex nature of this project, we won't be able to hit everything, but we've selected some that might be of the most interest. So to start out, we lay it out where it is on the site. The new Globe Life Field is directly south of the existing Globe Life Park in Arlington and directly to the east of the existing Cowboys Stadium. On the west side of the site is Johnson's Creek, which is an important site feature, which we'll get in on later in the presentation. Some Globe Life Field metrics. This is a $1.2 billion stadium. It's 1.8 million square feet, which does make it the largest in Major League Baseball. It's on a 13-acre site. It has 43,000 seats, and it is scheduled to open hopefully in July of 2020, albeit without baseball fans present. It has about 90 suites, 10 low suites, and 13 field level boxes to give various premium offers and various vantage points for those premium areas. For the project team, this is a joint venture between the Texas Rangers and the City of Arlington. HKS was the architect. Manhattan was the contractor, who will also be presenting some items related to the stadium. And Walter P. Moore was the structural engineer of record. To further go down into the design team, under HKS were 4 associate architects, VLK, VAI, SDS, and EGS. Walter P. Moore is the structural engineer. ME as the MEP engineer, WJHW as the technology consultant, MMA as the civil engineer, Land Tech as the geotechnical engineer, and SWA was the landscape architect. So one of the important features we wanted to get into was the site and the permanent retention system. So to understand this, we'll look at another view of the site, and once again you can see Globe Life Park here right to the north of the site. And here you see Johnson's Creek on the west side of the site. And actually there was a approximate 44-foot drop from the east side down towards Johnson's Creek. You can see that in the site grading here with approximately 579 on the east side and 535 on the low side. And there's even a little bit more of a drop as you go down to Johnson's Creek, which is just off the page here. And you can see that the service level is actually down at 506, creating the need for a grade separation of approximately 73 feet. So there was a unique opportunity to use the site here to the advantage. And it was done by creating 2 different street levels, 2 different grade levels. On 3 sides, grade was at approximately 558, and you would enter from grade onto the main concourse. At the east side, where the grade is higher, it was the final grade was also kept higher at 575, and you actually entered in on the suite level. In each case, you would enter into the field and actually enter into the stadium and actually look down onto the field, which is similar as the existing ballpark. We'll also note that there are some benches here where the excavation stepped out at some of the upper levels, minimizing the amount of square foot on the lower level and creating a need for a stepped excavation. So, given just the large amount of excavation, there was a need to create a system that did not deliver the large and huge amount of lateral forces from the walls onto the structure. This was done through provision of a soil nail wall. So what's shown here is a series of soil nails drilled, with the construction process being you would excavate down, install a nail, you would then put a shotcrete portion of the wall for the temporary wall. You would then excavate further, drill a nail, and put a shotcrete wall, and then complete the process until you're at the bottom. You'd install your waterproofing and drainage items. Then you would come back and you would build back up a permanent concrete facing wall back from the bottom up and actually put a separation joint between the retention and the structure, thus not delivering large amounts of lateral load to the structure. You can see on the right side, there's a version that shows the low and the high bench, with this high bench being on grade as well. And a lot of times you'd actually have floor structure residing in that area, providing additional surcharge loads on this low bench excavation. So the design criteria and system was coordinated between Walter P. Moore and Landtech, the geotechnical engineer, and eventually designed as part of a performance design by the design builder, who was Hayward Baker, for this project. So what did it take to build this permanent retention system? It was a whopping 1.3 million cubic yards of soil removed in this excavation, which was about 97,000 truckloads of soil. It was about 253,000 square foot of wall, had a 6 months construction duration, a max height of about 73 feet, and it is the largest soil nail wall in North America. Here is a view looking towards the west, and you can see here they have created this first bench down, and they're drilling in the first soil nail wall, in the first soil nails. You can also see beyond, where there's a series of soil nails already drilled, and they actually do have the shotcrete facing here. So they would continue this excavation and soil nail installation until they reach the bottom of all the entire excavation. Here's another view, and in this view you can actually see some of those benches here at this location along here on the west side as well. The max height is down at this corner. It's about 70 feet plus. And this actually has a view where the wall's at different stages of construction, with much of the cast-in-place wall being in place at the southern end, and at the northern end you can see it's not yet in place. And a final view, this shows the excavation mostly complete. You can see the trucks that were being used to haul away the soil. In addition, you'll see the temporary ramp on the far side, which was used to get man and materials down from the street level down onto the field. This will be a topic of the Manhattan contractor presentation, to discuss some of the coordination items between us, the geotechnical engineer, and the contractor to fill in that temporary ramp. They'll also be talking about other challenges regarding sanitary sewer installation, bore pits, and other water management considerations of this excavation during construction. Next, we'll focus on the overall building structure and understand what the different components are that go into this building. So the most fundamental being the systems. The lower two levels on this building are actually concrete, primarily comprised of panform beam and slab system, while the upper levels are made of steel with a composite floor system. And this was done for primarily construction schedule. Steel being a long lead item where it takes several months from issuing construction documents till the steel is on site, while concrete is a short lead item. So they can start building the lower concrete portions, and by the time they built those first 2 levels, they would have steel on site and be able to continue the rest of the superstructure with steel, which is a faster construction method, thus saving time, overall time and schedule. If we look at the typical building section, you can see here is the soil. This shows a benched excavation with the soil nails. And we have a service level which is actually on grade, followed by a lower concourse and main concourse, which were both concrete levels. Then we have a suite level, office mechanical level, upper concourse, and upper bowl, all comprised of steel. And finally, we have precast pre-stressed seating units that support, that comprise the bowl and provide an area to put the seats. For the first 2 levels of concrete, we have a 25-foot floor-to-floor, followed by a 27-foot floor-to-floor, which brings the main concourse up to approximate grade level. Another important consideration of this was the front portion of the bowl, which is actually completely made of precast. So you have precast rakers and precast columns, as well as the precast seating units. What this was done is to maximize the laydown area to help with the construction logistics. So this area can be left out during a construction of a majority of the ballpark, and since it can be erected very quickly, it can come in at a much later date and be installed after the contractor is able to remove a lot of the laydown area that they had. Next, I want to talk about a couple opposing design considerations for the structural layout. The first being what we call the street. So what is shown in yellow is a concourse area at the main concourse, and it is directly below this sloping roof, which is primarily comprised of ETFE, which is a transparent membrane that allows sun to shine down onto this area. Given the width they wanted for this street, it required that the column be inset here, which set this column, which then required a cantilever at the back of the bowl. What they were trying to create here is a very wide area, in which case there was concessions and restrooms on the left and a ballpark on the right to mimic kind of a street environment, similar to what you might see in Fenway Park. Well, at the same time, at the service level, there needed to be a service corridor that provides a fire lane as well as a corridor for various utilities and operations circulation, which set the location of this column here. And what resulted is in the need for a sloping column between those 2 columns here. And we also have shear walls on that grid, which then created a need for sloping shear walls as well. In order to get the seating bowl as close to the field as possible, we had a 35-foot cantilever, which was accomplished through the provision of a 2-story deep truss. The back truss had about a 9 feet cantilever, but had a large depth of approximately 20 feet. As mentioned, the overall goal of the project was to get the seating bowl closer and provide a more intimate environment. You can see the outline of the new Globe Life field in comparison with the existing Globe Life Park in white and blue. You can actually see that Globe Life Field is approximately 20 feet closer to the field at the upper levels. And actually you see also at the lower levels, they are also several feet closer, providing that more intimate environment that was desired and bringing the fans closer to the action. Here's a picture of that sloping grid we talked about. And you can see here the workers are actually forming one of those sloping shear walls in this picture. And here's a couple final pictures of this shear wall is actually in a formed condition. Here's some to report. Along with this is a good picture of that sloping shear wall and column grid in the final condition. We also see here a view of the steel and some of the precast pre-stressed seating units installed and at the various stage of construction. You might also notice these columns have these little corbels attached to them, and those are for where the precast beams can come and be erected and sit on those corbels. So you can just see the precast area resides in about this area. You can see the amount of extra laydown area the contractor was able to achieve through coordinating this precast system down low. And this is yet another view of that just represents the complexity of the steel raker system needed to support the seating bowl. This is a rendering of the street that we had discussed, and we do not have any professional photography yet on this project, that we haven't been able to get them out there due to COVID concerns, but it does give a good representation of what they're trying to achieve. You can see the skylight element provided by the ETFE up top, and the field is over here to the right with concessions on the left. And we do have a construction photo of what this looks like installed without the finishes, but you can see what that skylight would look like in the final condition. One other important item we wanted to discuss was the north bends, and you can see those here. This is on the north side of the ballpark in the Texas Live Plaza, which is the entertainment district directly to the north of the ballpark. This features a concert venue, which is nestled right here just to the north of the stadium, as well as several shops and eateries. The north wall here is featured by large expanses of transparent curtain wall, and approximately every 60 feet you'll see these bents that incorporate the arches, which are an homage to the existing ballpark arches as well. And while these have an important architectural feature, they also have a very important structural role as well, in that they support the rail truss for the retractable roof. And here you can see another version. So what we want to do is first focus on the steel levels of this area. So you can see that there's a rail truss right here, and the retractable roof actually rides on a rail that sits directly above this leg, and then through the provision of a box truss, this all goes down to a truss structure down below that then takes all the load into the below structure and into the ground. That structure is about 100 foot tall. It has 16 feet deep cross trusses, which are 30 foot deep at the end. And in the middle, you can actually see an inverted home plate area that we created. That's actually to route a large, several feet MEP duct that actually brings the cold air and circulates the air into the ballpark. Each one of these bends takes about 1,600 kips of dead load and 600 kips of wind load, and as a result, lots of these legs here are W36 by 487s, which makes this quite a large steel structure needed to take that type of load down to the ground. Here you can see some photos of those during construction. And here in this photo, you actually see those arches really start to take form even before the cladding has been erected. And finally, you see this photo where actually you can see on the outside they have started setting in these brick inlaid precast elements that form those pillars that you see from the outside. Another important consideration as the north bends was the integration of the ramping system needed for patron circulation. So you can see here, this ramping system actually transitions through the bents in various manners depending on what lever you were at, resulting in the need for various configurations of these north bends depending on where you were on the ramping system. And while this was a very important design consideration given the different stiffnesses and strengths of each one of these different trussed elements, it also had some coordination needed with the contractor below for them to help set their jointing needed with their construction sequence, which was a large coordination item between us and the contractor that I believe they will also cover in their presentation. And what you have here is the final condition. You can see the outside edge of those pillars with that brick inlaid precast with the large expansions of curtain wall in between. We also want to talk about the north concrete rakers. And we're focusing here on the lower bowl portion. We have precast rakers below for the reasons mentioned before, and cast in place rakers and structure above, along with MEP openings as well. We have approximately 30-foot cantilever at this location with a 12-foot 6 deep raker and an 8-foot deep backspan, approximately 15 feet deep at the link beams and 16 feet deep at the legs, which then reside on an 18 by 18 by 8 foot 6 deep cap set on 4 48-inch piers. And here you can see kind of a final look at those rakers and another view from the vantage point of the rakers. And this gives you an appreciation of just the amount of construction logistics and the amount of cranes needed to erect this bowl construction. And you can also see, just get an appreciation for all this area that was left out around here, that precast that was left out to provide more laydown area for the contractor. So what did it take to provide this building structure? It was approximately 10,000 steel beams, 850 piers, 750 columns. There was about 10,000 cubic yards of concrete in the lower concourse, which is about enough to fill 3 Olympic-sized pools, 6,600 cubic yards of concrete in the columns, and about 70% of the seats are between foul poles, giving most of the seats excellent vantage points to the field. For the bowl steel alone, there was 16,000 tons of steel needed. The structure sits about 100 foot above grade. There was 12 cranes needed to erect the bowl items alone, and the footprint of the stadium was approximately a little over 800 by 1,000 feet. One other item we wanted to discuss was the Northwest Videoboard, which you can see here in the rendering. And it does appear to seemingly float out over the edge of the stands in this rendering, which in the final condition in this photo you can actually see is the case. And once again reinforced in this Revit model. So how is this achieved? First of all, the board was 110 feet wide by 42 foot deep, and it did have a 45-foot cantilever at the end with a 30-foot backspan. And of course, to achieve this cantilever, you have to resolve the vertical loads needed, but you also have to resolve those lateral loads, that horizontal wind sail effect that you get from the wind loading. First, to resolve the vertical loads, we provided this blue in-plane truss needed for that vertical cantilever resistance. But we know we also had to resolve that out-of-plane load as well. To do that, we first provided the out-of-plane braces in yellow, shown here, that help resolve that load down into a horizontal truss in green here, that then can take it down into the vertical lateral load resisting system. Additionally, there's a series of horizontal trusses at each catwalk level, as well as a vertical truss at the end of the scoreboard to help tie all those together. And here we can see what this looks like in real life. First, we see a series of vertical truss in the scoreboard itself to resolve that vertical load. We then see a series of out-of-plane members that help resolve that lateral load due to the wind. We actually can't quite see the horizontal truss that then take that down to the vertical lateral load system, but it is in this plane here. We also have a series of horizontal trusses at each catwalk level and a truss here at the end that then tie all the scoreboard elements back to this out-of-plane bracing. And what you have as the final condition is something that looks like this. And here you can actually see it with the video panels installed. So finally, we wanted to talk some about model-based delivery in our collaboration with the contractor Manhattan on this, and this is something they'll also be covering from their perspective as well. So what you're seeing here is a typical raker frame that's fairly repetitive around the bowl, and what we've actually done here is modeled every piece of rebar that goes into the beams and columns. So you can see a sloped raker along with several circumferential beams, more horizontal beams here at the back along with one of the sloped columns and a series of other columns. We also modeled this to coordinate with the various anchor rods coming down from these braced frames. So we modeled this in order to be able to solve problems virtually through this process before they become a problem in the field. And it was used between us and the contractor to solve those problems and to help move the schedule along. Additionally, on the north part of the building, not only did we model it, we also modeled the north part and provided shop drawings and bar release files to the fabricator. So here we can see a condition where we have these north bends that we were talking about that support all the vertical and lateral loading of the roof, and they're coming down on these concrete elements, which then take the load down to the ground. In this case, we have the very large vertical and horizontal elements. We also have a horizontal return shear wall here as well. So once again, we modeled, for this process, we would model all the rebar, ties, vertical steel needed in all these elements. We would coordinate them with all these anchor rods you see here and get those bar spacings where they needed to be. We then create the 2D shop drawing as well. So in the field, they would have both the 3D and the 2D shop drawing. And finally, we would actually take those and we would provide the bar release files directly to the fabricator so they could fabricate off of them. Here's another example at the north area where we have a raker beam coming down, and you can see the various ties sloped in different directions along the steel beams in multiple directions, column joints, and so on, with the representation of the 2D shop drawing on right. And once again, we provided the bar release files for this directly to the fabricator. And finally, we'll go back to the important subject of those north bends where all that load is coming down. So here you can just see the complexity of the joint that's happening here. On the left, you can see the model of the steel with over 20 anchor rods coming down, each of them being 2 to 3 inches in diameter, with a large amount of reinforcement that's needed to resolve all the loading coming down through these legs. So once again, we modeled this and coordinated this. The contractor is able to use it to help place their reinforcement effectively and get the anchor rods coordinated with those locations. We also knew that this was a very important area that we just couldn't mess up because the fix would be very difficult. So from that standpoint, these intricate templates were actually also built by the contractor as just a temporary way to get the anchor rods in the correct location and keep them in the correct location during concrete placement. And through this collaboration, we can actually say that none of the anchor rods at the north bends were mislocated at all, creating a very efficient and fast construction of those elements without any issues. You can also see another view of the north bent steel here as well. So what are we trying to accomplish with this model-based delivery? So we've shown that we can model the rebar, including the hooks and terminators and the reinforcement columns and any beam MEP penetrations. We can also coordinate those with anchor rods, bend bed plates, and any of the other special conditions that are needed. And what we're trying to do here is we want to solve the problems virtually before those problems in the field arise, which eventually happen on every job. And we want to figure it out virtually. It positions the team to make better decisions when confronted with those discrepancies and helps reduce the risks and project schedules. By us modeling the rebar, creating the shop drawings directly from that rebar, providing the bar release files directly to the fabricator, we're able to remove the silos that often are created in that concrete design and review process that helps us protect project schedule, reduce risk, and provide more quantity certainty to all parties. With that, we will turn over the control to the next portion for the roof portion of the presentation. Thank you very much.
So let's talk about the roof part. So we'll start by talking some terminology as far as, and you'll hear these throughout the presentation. So on the north side of the screen, you see the north rail, and the south end, you see the south rail. And then you've got the fixed roofs. These are the roofs that don't move. On the east side, shown in dark green, and then on the left side, shown in a brighter green bluish color. And each one of these also have the planar trusses that obviously frame into them and their associated bridging and framing. And then you've got the operable roof that sits on top of the west roof and then kind of comes to the side of the east roof. And this is the closed position. And then you have a series of catwalks within both fixed roofs and the operable roofs that they also have access to each other. And then finally, you see the roof at its open position. So the roof, as far as the dimensions go, the north rail truss is 938 foot long. The south rail truss is 945 foot long. The span from rail to rail, and this is the span of the operable roof as well as the span of the fixed trusses, is 642 feet. The operable roof is 416 feet wide. And then it takes about 10 minutes or so for it to move depending on the wind, and then about 2 minutes or so for the seal compression. So the whole process takes about 12 minutes to move the entire operable roof about 405 feet. Here's a picture of the rendering on the inside that you can see the operable roof closed, and you can kind of see on the right end it kind of comes to the side of the east roof. And then here is what the rendering shows it being open. Here's another view looking towards the west, and you can see the operable roof completely slides over the top of the west roof. And here's a picture of the final condition, it being built at the closed position. Another view of the structure from the outside with the roof closed. And this is, again, one of the renderings from HKS. And then this is another condition with the roof open. It's really cool how it kind of creates this little shaded area here that potentially could be used for some other things. And here is one of the one of the drone footage, or no, this is from the live cams that Manhattan had that kind of shows you at the final stage how it looked like and at its open position. So tonnage-wise, the east roof had 2,600 tons of steel, the west roof 2,000 tons of steel. The north and south rail trusses combined had 4,400 tons of steel, and the retractable roof had 10,000 tons of steel. So that's a total of 19,000 tons of steel, which is about a little more than 2 times of what you had in the Eiffel Tower as a comparison. So we're not going to get too much into modeling and analysis due to time, but just know that the whole thing was parametrically modeled to meet the constant change that was happening during the design phase, and then also to meet the schedule. So we needed to parametrically model the whole thing to kind of match the surface that HKS was providing to us during design. As then it was changing, the trusses and the model would adapt to it. And the other thing to also point out that was extremely useful is naming everything, which internally we call indexing. This indexing essentially ended up in the drawings to point out connection forces and also connection concepts and sizes, etc. So this was very useful, and this was all done parametrically, so we didn't sit there and name each one of these elements, but we would be able to know exactly what element was where just based on its name. So we'll move on from that part of the discussion, and then so let's take a look at closer look at the structure itself. You've got the east box truss. The east box truss has 19 planar trusses that frame into it, and then in orange you'll see the purlins and bridging and bracing that kind of come in between. The east fixed truss spans on the south end, which is to the right of your screen, to a truss structure that during design we called it the colossal column, and it kind of made it out and everyone started calling it the colossal column, which I'm okay with. So that's around 125 foot span, and then from there on to the north box truss, it's 517 feet. At each end, on the south and north, you've got the knuckles. Essentially, that's where the connection happens from the fixed roof to the north truss and south truss. The planar trusses span on one end to the bowl framing, and then on the other end to the box trusses. You will also notice that on the east side, we had 2 columns that the roof spans to. On the back end, we released the connection to essentially not allow this truss to act as a, for this back support to act as a backspan. The other thing you'll notice is that there is quite a bit of depth here, and most of that is architectural. That 75-foot deep member also wants to roll due to wind and other phenomena. So the planar trusses essentially act as roll beams to prevent it from rolling over. Here's a picture of how during construction it was constructed. Both of the box trusses were constructed from the south end. There were 2 shoring towers that were installed. Actually, there were 4 shoring towers that were installed, 2 on the east side, 2 on the west side. And then they started from the south end, 3 stages. The boxes were being built on the ground, and then they would go up in stages. Here's a more completed picture. As you can see, all the planar trusses, bridging and bracing are all in place, framing into the box truss on the east side. And here is the final condition that you can also see the ETFE panels as well as the Texas Ranger sign. From the inside, you can see the scoreboard, which, by the way, the scoreboard, I don't think I mentioned, is 152 feet wide and 58 foot tall. On the west side, in a similar manner, you have the box truss that spans, on this end, it actually spans fully from north to south. And we've got 24 planar trusses with 30-foot spacing, and then the bridging and bracing in between them. So that, again, is a 642-foot span. It's 61.5 foot deep, which is shallower the east roof. This is mostly structural. It's not so much architectural. One of the cool architectural feature that it was able to achieve is that if you look, the designers from HKS wanted to be able to, essentially when you look from the bottom, you kind of think that these planar trusses, depending on where they are, spanning 55 foot to 127 feet, kind of look like cantilever because you can't see the box truss when you're sitting from below. But in reality, they're spanning to a box truss that's spanning from rail to rail. Here's a picture of the west roof during design, and again, you can see the shoring towers for this end, and you can see the shoring tower on the east side, so they were kind of both going side to side. And then on the left side of this picture, you can see that Jeff talked about the ETFE over the street and that framing going on. And then towards the bottom of your screen, you can obviously see the rails. So with that, let's talk about the rails, and we'll move on to the operable. So the rails, on the north side, as discussed before, it's 938 foot, and then at the end of it, you also have a 100-foot cantilever, which was an interesting design challenge. And these trusses had to be extremely stiff just because of the fact that you have an operable roof rolling over them with the load that's coming from the operable roof. And the trusses sit on the bowl structure, so the geometry of the trusses, of these box trusses, had to be determined also based on what kind of support we had below. Jeff talked about the north end. Specifically, they sit on these bends, which again, the design of the bend and its stiffness was challenging. And then on the south end, it's mostly the bowl structure on columns that they come up. And then towards the west side is where you also have three bays of bends that are similarly constructed. You've got 4 knuckles where the fixed roofs come in. The north end, both sides actually, are 25 feet deep. Typically on the north side, they're 33 foot wide. On the south end, the typical bay is about 25. And depending on where we landed on the column, we had to obviously modify that. Here's a picture of one of the knuckles that kind of shows you a sense of scale and complexity of what these connections look like. This is on the northwest side where the west fixed roof comes in. And here's a cross section from the drawings, and one of the things you'll notice is that there's a 15-foot drop from the north side, which is shown on the left, and the south side, and that had to do with the fact that there was a shape that HKS was trying to achieve, and then on top of that, we had this 20-foot tall 4-bar linkage that we'll talk about in a little bit, and the reason that existed. So as far as the rails themselves go, we had these rail girder assemblies. Essentially, it was plate built up construction sitting on top of these W36. So this was both for gravity and the lateral loads that were coming from the operable roof to be received and then essentially get transferred to the box trusses. The rail girders was 37-inch sitting on W36s, so it provided the stiffness that we needed to control the deflection and also vibration that the operable roof needed to be able to be operational. And one other thing that's cool about the rails is the fact that it's using an A150 crane rail, which is the second largest produced, and it's about 100 pounds per foot. And there's about 1,800 foot or so of rail length total used on the job. So that's another interesting fact. Here's a picture of the north rail once it was being constructed, and again, you can see the scale of that 100-foot cantilever with its 60-foot backspan. And then here's a picture of the south rail once it was mostly completed. Another picture of the north rail. You can see the scoreboard that Jeff discussed earlier in the picture here. Also, you'll see the bends that the north rail kind of spans in between. And a cross-sectional look. This is on the south end, and north end similarly. We have these really wide platforms. Obviously, a portion of that will be taken by the feed rail, but essentially provides room for Unisystem to be able to maintain this system. Essentially provides them enough clearance to drive their carts in this space. Here's a picture of the rail girder assembly. You see these holes. These are access holes to be able to reach to the bolts and adjust the rail as needed. The rails are interesting because they're essentially the same thing that you would see in a normal train rail. So they use a process called the thermite welding to weld the pieces of rail that come in, and they essentially grind them smooth so you won't be able to tell, so that the wheels as they travel over this won't experience any difficulties. So moving to the operable roof, we've got 5 box trusses, and in between them you have the bridging and bracing and the purlins that come in between. The operable roof is skewed 15 degrees, and it's over 20 million pounds and roughly around 6 acres of area wide. The yellow region that you see on the left is the ETFE portion, which is the clear part that allows light to come in, natural light to come in. And the operable roof spans 642 feet rail to rail. At its deepest points is 65 feet deep, and it kind of narrows down to a 59-foot deep. The clearance from from the field is 209 feet. And that was based on the study that HKS performed to make sure that the ball projection doesn't hit the roof. And then you also see the 4-bar system on the south end, which allows for the movement. And that the importance of the 4-bar is the fact that if you look at it in this picture, it allows for up to 24 inches of movement. This reduces the amount of stresses that gets transferred from the operable roof down to the bowl system and the rail trusses significantly for various reasons, whether it's wind blowing on it or it's temperature blowing on it. And these systems sit directly on top of the rail girder systems. So as far as the mechanizations go, we've got 10 driven bogies, 6 of which also have a clamping mechanism. And the remainder are idlers, that they're just wheels that get pushed. So on the south end, again, this is where we have the 4-bar system, and you have the two-way bearing, ball bearing system to allow for movement in both directions. And the reason they're both ways is because of, again, of that 15-degree angle to allow movement in both directions. On the north side is essentially our fixed side. That's the side that doesn't move. And you can also see the bogies. Each bogie has 6 wheels that it's essentially the bogies are that a traction system, essentially similar to your car, that you've got the engine that moves a smaller gear, and that small gear moves the bigger gear, which is connected to the wheel, and then it rotates that, and that friction between the wheel and the rail, it's what's causing it to move. Each one of these, at the total load, the static load, so we've got the static load and operating load. The static load is around 21,000 kips, and then the operating wind, under operating wind, which is around 40 miles per hour, is around 1,700 kips on each bogie. There are a total of 120 wheels, and each wheel is around 36-inch in diameter. The motors are 10 horsepower, and it's around, the total roof horsepower is around 800,000 foot-pounds of torque. You also got 2 spring per wheel assembly, which adds up to 240 of them. They're these polyurethane segmented spring that are 12-inch in diameter each, and they allow for about ½ an inch in compression to make sure that at all times the wheels are in contact with the rails. Another interesting thing about the bogie and the mechanization system is the fact that they have a regenerative system, that when the roof is, let's say, is coming to a stop and there is a big wind blowing, it regenerates. It's similar to an electric car, that when you stop, the electricity is generated and it's put back onto the grid. Also on the left side, you see this clamping mechanism, which the clamping mechanism is also pretty cool because it's connected to the electricity, and it has this magnetic system that in case the power goes off in the middle of the move, the clamps essentially engage because it's the magnet is no longer engaged, it's an electromagnet, that when that's gone, it clamps back and brings the whole roof to a stop, which is considered the emergency stop, which we'll talk on in a little bit. It causes this roof quake behavior because about 5% of the weight of the roof now wants to act laterally. So here's a picture of the wheels in Unisystem's shop as they were building them. You can see that smaller gear that we kind of talked about that's connected to the motor, and you can see the motor assembly on the right side. That's where the motor gets attached and moves that smaller gear, which then moves the bigger gear. And then here is the one bogie assembly with the motors being assembled in Unisystem's shop. And here's what it looks like when it makes it out to the storage area that they had on site as they were being delivered. Then it got lifted up with the crane and was brought down to be placed on top of the rails. And you can see on this one, you also have the bumpers that are being connected at the end. And this is kind of what the process looked like as you were kind of bringing it down very slowly to make sure that all the wheels connect to the rails. You can see there are these rods that are being installed, because what's also interesting about the 4-bar system is that the whole roof is being erected in a cambered position, and then when you release the roof and you decenter it from the shoring tower, it goes back to essentially a 90-degree position, which as it was intended. So these rods essentially allow you to control that rotation at each bogie for its cambered position before it receives the operable roof. And here in this picture on the right side, this is a more completed stage. You can see the feed rails that essentially carry the electricity that comes from the grid. In this picture, you can see the big red button that engages that whole e-stop mechanism, the emergency stop mechanism. So if the power goes off or you hit this button, both of those bring the structure to a stop. And if that doesn't work, we also have these bumpers that come to this structure that connects to the rail. And hopefully that doesn't happen, but it's designed so that the roof doesn't slide off the side of the building. But both of these create a large level of force that the structure had to take. On the top of these units, you also see these little cabinets areas. That these cabinets on the right, you can see that include these wheel box assemblies. And on the top, you can also see the springs that we were talking about earlier, that they essentially slide down. There are cranes installed on top of the roof that you can move the roof and essentially park it where these cranes are, and then lift up one of these wheel boxes as they need to be maintained and changed. So then you get one of these huge cranes, which I'm sure Manhattan will probably talk about a little bit about this as well. And then you lift up the boxes that are the operable roof boxes, and then you place it on top of the mechanization platforms. This is on the north side, so unlike the fixed roofs, the operable roof was built from the north end, given the north end was the fixed side, and then was essentially built. And then the other thing to note is that the shoring tower that was used on the west side was disassembled and moved slightly east to allow for these roof box trusses to be built on top of it. And then as they were being built, they would move them to the side and then use that same shoring tower to build the next segment. And then essentially little by little, you had, as these box trusses were being assembled, they also had cranes that were building the planar trusses in between them until you had the full structure built. Here's a drone shot that shows you the final condition. It's kind of in an open position. Another picture with a drone shot showing and this is from a picture from below that kind of shows you it's the operable roof spanning from side to side, and this is probably the worst condition that this cantilever could see. The other interesting part is that this whole system really requires one person to operate it. He sits in his operation with a couple of spotters on the rail, making sure that everything is going smoothly. Here's a picture on the top. You can see the ETFEs as they were being installed. And this is after they were filled with air. One cool thing about the ETFE, as you can see in this picture, is since they allow light, in order for the light to not bother the eye of the pitcher, there's this patches that are installed inside, one at the top and one at the bottom. And if you see from the bottom, you can kind of see that they're on one end on the top and then the other side at the bottom. It allows for the natural light to come in, but it prevents it from hitting the eyes of the players as they're playing. You can kind of get a better picture of it here, that you can see that the first base is kind of clear and there's shadow. You can also see the gutter system and how it gets drained out on top of the rail and then down to the ground. And I was asked not to talk about the analysis much, so I'll skip most of these. Just know that there was a wind tunnel study that was done on the structure. You can see on the left, these are the pressure taps that RWDI did the wind tunnel study. These pressure tabs were essentially the things that they had in the mock-up system that they built, and then they measured each tab, and then we were able to map all those pressure tabs to our structure and our analysis model and apply the wind loads directly to the structure. The RWDI studied the model in open, closed, and half position, and those were the conditions that were studied at essentially all the different conditions. Essentially, the roof could be parked at any location. One of the analysis things that we talked about was this whole bumper mechanism and also the e-stop mechanism that both acted like an earthquake, essentially, on the entire structure. That added complexity. The 4-bar lean obviously added complexity because you have different types of structure essentially sitting on your building, from the forces that the roof itself experiences as well as the forces that any supporting structure experiences. So we also had to analyze all of that. And then on top of that, like I mentioned, the roof could be parked at any of these conditions with the full load. And then there's the operating load that as it moves. So we had to essentially create these travel path graphs to understand the behavior of each one of the wheels, each one of the bogies, and also the different truss members that were experiencing the different loads. So we had all sorts of studies that were done with these graphs that would show what the structure is doing as a whole. And with that, I will conclude and we can take any questions.
Hey, Borhan. Thank you for presenting. Thank you, Jeff. This is a great presentation.
Sure.
I have a question. So obviously on every type of project, you know, you face issues as far as some things go perfect. Some things just kind of don't quite go as you planned. On something this complex, I know you touched a little bit on how you all did the rebar modeling, but are there some lessons learned that you can share with us, either on the design or on the management, that maybe you would kind of do a little bit differently if you were to do it again?
Yeah, sure. I can answer that question. I mean, as we get farther along the line, we always want to find new and better processes to help streamline the design process, and ultimately that provides multiple benefits down the road. And one is we want to continue to push the use of technology through parametric modeling, which is still relatively new in the structural engineering realm. And so that would include things like parametric modeling earlier of all elements. We want to continue to remove those silos between the design and construction team and be able to work more closely with them through rebar modeling and erection engineering, through multiple other things that we can partner with them on. That really helps remove those silos and provide a more coherent product and work product between us. So I would say those are the, we pushed those forward on this project, but those are the items we would want to really try to continue to push forward.
Mohan, Jeff, this is Mark Boyd. Is there anything unexpected you ran into in some of this modeling, the wind modeling, or some of the other the other aspects of this that you really didn't expect to learn, and maybe that you could share for us?
Well, I think one thing that I learned a little bit out even more here is the coordination needed in the ground for these. And, you know, as structural engineers, we have to be very focused on superstructure a lot because there are a lot of items that are required. We had concrete level, steel detailing, concrete detailing, multiple early packages, shop drawings come in while we're still trying to design, all the while that there's foundations going in the ground. And there was a lot of coordination that was needed for items going to the ground, various civil sanitary sewers, grease traps, other things that we had to, because we were so far out of ahead of everyone, and the contractor was having to build our items out in front of everyone, we kind of ended up having to coordinate those a little bit on the fly as we went at that ground level. And I think the contractor might hit a little bit on this as well. So just the coordination of all those items in the ground that might get close to our peers, and just how they affect our items and how we affect their items, was something that just requires close coordination that always isn't at the forefront of the project schedule at the beginning.
And another thing I'll mention from an analysis standpoint is really the sheer magnitude of how much analysis needed to be done. Because as you can tell, there's all the different wind conditions, and then you have to combine those with different scenarios that we kind of touched on, the whole e-stop and the leaning of the roof and the bumper. All of these could be combined differently. And then on top of that, the fact that the roof could be parked in any position, it creates a challenge in the sense that I think at some point we had some 28 different computers running analysis at the same time. And obviously we couldn't stay up all night, so we had to write these programs that would run a analysis in one of these models in one of the computers that we had. And these spreadsheets, it was essentially a macro that we had created to communicate with our SAP models through API that would run it and export the results that we needed, and then move it by a foot, and then run it again, export the result, and then do it again. And then do that 405 times in all these different models that I think we had, I don't remember exactly, some 30 plus different models that we were running. So we had to come up with like crazy schedules, figure out who's doing what, and also at the end of it, what do you do with all that data that you get? So we also had to get creative with how to understand and manage the data that we receive. So it was interesting.
I got one last one. You mentioned that for the bowl structure, you left out part of the structure on the phasing just due to construction. Well, I'm just curious, was that coordinated between y'all and Manhattan? And was there ever any other kind of phasing that y'all maybe considered?
Yeah, I mean, we did have the benefit of Manhattan came on while we were about 5 or 6 months in the design process. And yeah, there was numerous items that we worked very closely with Manhattan to coordinate regarding various phasings. I mean, there was a temporary ramp condition. There's that we talked about earlier. Borhan showed the erection procedure there. I mean, that has to be closely coordinated with the contractor as well. So we coordinated that. Obviously, packages, I mean, they have concrete and steel. Concrete actually, you know, constructs first, but they actually had to have steel packages first to get the steel on site in time to be ready for when the concrete was completed. So we had different sectors, different areas, different levels, And all this went into a master design schedule and construction package schedule to which we issued to help achieve the very aggressive project schedule, which was design and construction in 39 months. So there was a great deal of coordination between the two, and that a very important part of the process.
Thank you, Jeff and Bohran, for presenting on the design of Globe Life Field. It was great to see how the design was a collaborative effort and how the engineering process came together. Thanks for joining us.